and this is my lab 3. So the purpose for this lab is to use Newton's law of universal gravitation in glow scope to 1, find the mass of an unknown black hole, and 2, simulate a multi-body gravitational orbit to find an initial velocity of a spaceship. The system and surroundings for part 1, star and black hole, everything else. Part 2, planet, moon, and spaceship, while everything else is in the surroundings, and we'll be using glow script as a computational model. The physics principles, Newton's second law. We've been using this for the past 2 labs. We know F net is change in momentum over change in time. We can get the velocity update formula from that. I also included this because we'll be needing it in part 1, how you can change F net into its parallel and perpendicular components. And then finally, universal law of gravitation. We have this formula that we learned in class, and it's just the attractive force between 2 objects based on mass and distance. Okay, so for part 1, we have a starter code. We want to modify the code to find the mass of a black hole. How do we do that? Well, initial conditions, set gravitational constant, mass of the star, delta t, which I believe is time of a day in seconds. And then we have our initial momentum, final momentum, so we can get change in momentum. We put that over change in time, that's dp dt, which we know is F net. So then we can get our parallel direction by using this equation. The change in magnitude of momentum times p hat, which is this line of code, and then we can get our perpendicular direction by just doing F net minus F parallel from this equation. And then with that said, we can just find our mass of the black hole using the universal law of gravitation and setting it equal to mass, which is what this line of code is doing. And then I just coded my arrows so that they show each component. That gives us our results. As you can see, we have a rotational orbit with our 3 vector components. The reason why it got larger here is because the force got larger since it got closer in distance. So we had 457 different mass values being updated. I put it in Excel, averages to be 1.7 E34 kilograms mass of our black hole. Okay, what does this mean? What is the difference between F and dp dt? Well, mathematically, they look the same, right? Wrong. When you look at the right side of the equation, it's just an instantaneous equation. It depends on position. So the parallel and perpendicular components show how the motion should change. However, since we're doing a change over time, a delta t, that just means we're approximating the true rate of change. So as delta t increases, results become less accurate, and these components show how the motion did actually change. Okay, moving on to part 2. We're going to have a starter code, and this is our mission statement. We're going to want to modify the code and experiment around to find an initial velocity so that the spaceship revolves around the moon while the moon revolves around the planet. Again, here's our initial setup. I changed Tmax to be times 4, so it's 4 months. Okay, so we want to find Fnet on moon and Fnet on ship so we can update their positions. So looking at the moon, we want to find the F of planet on moon and F of ship on moon, which we use these equations, the position, and then we just universal law of gravitation. Same for the ship. You do planet on the ship and moon on the ship. It's just pairs, right? That's the big thing. Like, you're doing pairs. And then you update here, making them move. Velocity update, position update, velocity update, position update. And then here's what I've found through experimentation. X in the -15 and Y 43 for our velocity initial. And here's what that looks like. As you can see, magenta is our spaceship. It is revolving around this planet while revolving around the moon, which is revolving around the planet. And you can see that by this larger rotation while it has smaller dips revolving around the moon, showing that our initial velocity was successful. Possible sources of error in this lab. Well, our integration can accumulate errors over time since we have a larger time step, meaning each step is only approximation, and that approximation does not fully represent realistic situations as we are assuming there are no other forces, right? And that approximation also shows that our accuracy can diminish. Especially for part 2, there are various correct answers as we just use trial and error to find an initial velocity. To answer our final what if a system had a black hole, a star, a planet, and a moon? If we wanted to predict the motion, all of this, right? Well, it's sort of like part 2. We're going to want to go into more pairs of gravitation forces, black hole on the star, black hole on the planet, etc. And would there be any dominant interactions? Yes, there would, because we know our force equation is based on mass and distance. So the larger the mass is between 2 things, and the closer they are, they will have more dominant interactions, meaning larger force. Thank you for watching.